Hello. Hope I'm live. So we're going to continue in the paper Monosemanticity, Decomposing Language Models with Dictionary Learning. That's the full title. So the last time we read till here. So what we were discussing last was that the model could be small. This is the actual model, but we can make a bigger model such that the model is more interpretable. So before starting reading this, I'm just going to ensure that the stream is fine. Yeah, all good. Right, so what makes a good decomposition? Suppose that a dictionary exercise that the MLP activation of each data point is in fact well approximated by a sparse weighted sum of features as in equation 1. Alright. What makes a good decomposition? Suppose that a dictionary exists such that the MLP activation of each data point is approximated by a sparse weighted sum. The decomposition will be useful for interpreting the neural network F. We can interpret conditions under which the feature is active. That is, we have a description of which data points causes feature to activate. We have a description of which data points causes a feature to activate. Okay, so if we can find what are all the things that can activate that feature, yeah, that makes it a good decomposition. Okay, that makes sense on the diverse data set. We can interpret the downstream effect of changing the value of f in subsequent layer. It should be considered with interpretation 1. The feature explains a significant portion of the functionality of the MLP layer. Okay, a feature decomposition. What is feature decomposition? What is feature decomposition as in the Monosemanticity paper? Will this help? I don't know if it will. No. Refers to the process of breaking down a given feature or a concept of a model into components that map distinct, interpretable, semantic, meaningful attributes. Okay. I'll give an example. The term monosemanticity in the paper suggests that each feature should represent one and only. Okay, image classification. Imagine you have a transform-based model for image classification. Without feature decomposition, the model internal feature may mix various forms of the image. Through feature decomposition, the model is trying to modify so that its internal features represent distinct, independent aspects of the image. For instance, one feature might solely represent the shape of the animal, while another feature should represent background. Oh, okay. What is meant by feature here? Is it a bunch of neurons? That is, a feature activating means that a bunch of neurons are activating simultaneously. You did not answer yes or no. That's sad. Feature as a concept, feature as a pattern. Okay, you can say in all these forms. Yes, feature can be thought of as a patterns. Feature activation generally means a group of neurons. The goal of feature decomposition in monosemanticity paper is to ensure that each feature corresponds to a single clear concept. Yeah. Okay, all good, all good. So I think we are on the right track. Hmm. So okay, so feature decomposition. So we take different part. So a bunch of neurons explain if let's say an image which is easy to visualize, think of. So in an image, if the sky there is a sky or maybe a lot of the part is blue, the image probably like turns activates a feature which indicates sky or water. I think that's what the thing is meaning. Okay, so that is feature decomposition. Okay, a feature decomposition satisfying this criteria will allow to determine the contribution of features in the layer's output, monitor the activation, change the behavior. Okay, demonstrate that the network has learned certain property. Okay, we can do all this. Of course, decomposing models into components is just the beginning of the work of a mechanical interpretability. It provides a foothold in the inner working of the model, allowing us to start earnest on the task of unraveling circuits and building a larger scale understanding of models. Why not use architect's approach in time? Okay, we didn't read that. Probably it would have been fun to go through everything sequentially, but here we are. We highlighted several different approaches to solving superposition. One of the approaches was to engineer a model to simply not have superposition in the first place. Ooh, architecturally, like, okay. Initially, we thought this might be possible, but comes with a large performance with. Yeah, that is also what I am thinking. That is produced more with a greater loss. Oh, greater loss. I was thinking of a very big model. Even if the performance it has been too large to use in a practical real model, we felt the success of creating monosemantic models would have been very useful for research. And in a lot of ways, it's the cleanest approach. Unfortunately, having spent a significant amount of time investigating the approach, we have ultimately concluded it's more fundamentally not viable. In particular, we made several attempts to induce activation sparsity during training to produce models without superposition, even to the point of training models with one-hot activations. This indeed eliminates superposition but fails to result in clearly interpretable neurons. Specifically, we found that no individual neuron can be polysemantic even in the absence of superposition. Uh, yeah. Oh, this is a new extension I'm trying. I don't know if it's good or bad. Attempts to induce actor. Okay, summary was not what I was meaning. Uh-huh. Waiting for response. Still waiting for response. The content describes an exploration into the relationship between activation smart set. Okay. 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 I don't think that's. I think it's better. Uh. Okay. We'll go here and what is the difference between polysemantic and the superposition? Hmm. Okay, superposition refers to the phenomenon where a single neuron activation represents multiple distinct features. Okay. Polysemantic neuron are those that represent multiple distinct concepts but in a less obvious and ambiguous manner. Oh, okay. Superstition means that, okay, same neuron might represent dog and cats in different contexts, but you can't easily separate them. Imagine neuron that is supposed to represent ears of animals, but is also influenced by tails. It may not explicitly combine the concept in a very as in superposition, but in practice it is ambiguously capable in both at different times. Summary. If multiple features are combined into a single representation within the same neuron, thus it's a mixture of features that can be hard to disengage. Monosemanticity refers to a neuron that represents multiple features but in an ambiguous or context-dependent way, without clear separation between them. Okay, I'm just going to put you somewhere like here, I guess. Right. So to understand this, consider I model with a single neuron trained on a dataset of 4 mutually exclusive features, each of which makes distinct correct prediction for the next stack and labeled in the same fashion. Further, suppose that this neuron output is binary. It either fires or not. When it fires, it produces an output vector representing the probability of different possible targets. We can calculate cross entropy loss. Because the loss in the lowercase 2, okay, model achieve better performance by making it solve neuron polysymmetric, even though there is no superposition. Superposition. What is the difference between superposition and polysemantic? I think I'm still confused there. Multiple distinct feature concepts simultaneously overlaid within the same neuron activation. Distinct concepts in a less obvious or ambiguous manner. Even in the absence of this neuron can represent features, but these representations are not clearly separated. Okay, ears and tails. Single activation got different meanings. Suppose the image classification model, single one represents both furry and four-legged concepts. If both concepts are activated at once, you can easily decipher whether the neuron is capturing just the concept of fur or legs. So operation happens when multiple features overlap with the single activation pattern, leading to a lack of clarity in representation. Polysemantic neuron might represent multiple features, but unlike superposition, these features are not simultaneously combined. They are represented ambiguously, leading to unclear or mixed activation depending on a context. So I think polysemanticity means it is supposed to represent ears, but is also influenced by tail a bit. So it's kind of confusing. But in superposition, one neuron like represents its FR and legs. Okay. I mean, did I clearly understand it now? But I think we can move on. But if you push, okay, but I'm going to skip this part. Based on the reasoning and the result of experimentation, we believe the models trained on cross-interpret laws will generally prefer to represent more features polysemantically than to represent few true features monosemantically, even in the case of sparsity. Model trained laws other loss function don't necessarily solve this problem. For example, means may achieve same loss for both. Okay, not however. Then blah blah blah. Okay. Using sparse order to find good decomposition, there's a long-standing hypothesis that many natural latent variables in the world are sparse. Now, although we have a limited understanding of the features that exist in the language model, these examples we have are suggestive of highly sparse variables. Our work on triomodal superposition shows that a large set of sparse features could be represented in terms of direction in lower dimensional space. Large set of sparse features could be represented in terms of direction in lower dimensional space. Okay. For this reason, we seek decomposition which is sparse and over complete. Since okay, what I'm trying to guess this thing is trying to convey to me is neurons can be polysemantic. So we need to decompose them to sparser features. This is called the okay. How is feature decomposition performed in the paper? Several analytical and experimental techniques. I don't know, man. Although we have a limited understanding of the features that exist in language model, the examples we do have are suggestive of highly sparse variables, so that the large set of sparse variables could be represented in terms of directions in lower dimensional space. Okay. For this reason, we seek a decomposition which is sparse and over complete. This is essentially the problem of sparse dictionary learning. Now, in that sense, we are not only asking for a sparse decomposition of the activation, yeah, we make no use of the downstream effect of D on the model's output. This means that we will be able to use those downstream effects later in the later sections. So, I want to understand why making the problem more complete, which means initially sound trivial, like a trivial change, actually makes a setting very different from similar approaches. Okay, it's closely connected to why dictionary learning is such a what is dictionary learning? Machine learning techniques use to learn a dictionary, a set of basis elements that can efficiently represent the data through sparse linear combinations. Oh, okay. often is a signal processing computer vision NLP tasks like compression. Uh, okay, man, I'm going to skip this part also. Like this thing is very difficult. So I'm going to skip everything I don't understand, and that's okay. Despite this difficulty, there is a host of sophisticated method of dictionary learning. This method typically involves optimizing a relaxed problem or doing greedy search. We tried several of these classic methods, but ultimately decided to focus on a simpler sparse autoencoder approximation of dictionary learning. Okay. Wait. Despite its difficulty, there are a host of sophisticated methods for dictionary learning. Okay. Method of optimal directions of frame design. Algorithm for designing outcome to dictionary. Okay. These methods typically involving doing something. Okay. Wait, but involving optimizing a relaxed problem doing greedy search. Greedy search. Okay. We tried several of these methods, but ultimately decided to focus on simple autoencoder. Okay. This was for two reasons. First, fast autoencoder can readily scale to a very large data set, which we believe in is necessary to categorize features trained on large and diverse corpus. Secondly, we have a concern that iterative dictionary learning might be too strong. Hmm. So you're saying that sense of being able to recall just give me 1 second. All right. So despite the difficulty, um, this method typically optimizing relaxed problem or doing greedy search. We try several of the classic method, but ultimately decide to focus on simple automated approximation. Two reason. Okay. Secondly, we have concern that iterative dictionary learning might be too strong in the sense that it may be able to recover features from the activation which they cannot access. Okay. So Psi probably doesn't have these problems. Okay. Mm-hmm. A contrast path learning is very similar to the okay, that's true. And should be similarly powerful to recover features from superposition. Okay. Just ensuring I'm audible. Wait, am I not? Hello? Yeah. Okay, I don't know. Okay, sparse autonomous setup. We briefly overview the architecture and training of the sparse autoencoder here and provide further details on basic autoencoder reading. Oh, Okay, I'm going to, okay. Our sparse autoencoder is a model with bias at the input, a linear layer with the bias in the input, linear layer with the bias and ReLU for the encoder, and then another linear layer for and bias for the decoder. In time model, we found that the bias was quite important for autoencoder's performance. Oh, I didn't know that. Uh, our sparse autoencoder is a model with a bias in the input, a linear layer with bias and ReLU for the encoder, and another linear layer and bias for the decoder. Okay, I'll also put you there. We train this autoencoder using Adam optimizer. To reconstruct MLP activation of a transfer model with MLE loss plus L1 penalty to encourage sparsity. So that is the thing here. Okay, you can also copy that and wait. MSC loss, MSC not loss. Oh. Uh-huh. In training, we found a couple of principles to be quite important. First, scale really matters. We found that the training of an autoencoder on more data made features subjectively sharper, more interpretable. In the end, we decided to do 8 billion training points. Okay. What am I doing? Second, we found that the course of training some neurons cease to activate even though across a large number of data points. We found that over the course of training, some neurons cease to activate even across a large number of data points. We found that resampling these dead neurons during training gave much better result by realigning model to present more feature for a given autoencoder layer dimension. Okay, sure. Our resampling procedure is detailed in neuron resampling, but in brief, we periodically check for neurons which have not fired in a significant number of steps and reset the encoder weight in the dead neuron to match data points that the neuron can represent. Okay, sure. Advice for training sparse neural networks. Boom. Oh, oh, oh. How can I tell if the autoencoder is working? Usually, machine learning we can quite easily tell if a method is working by looking at an easily measured quantity like test loss. We spend quite some time searching for equal metrics to guide our efforts here, but unfortunately, I've yet to find anything satisfactory. Ooh. We began by looking for information-based metrics so that we could say in some sense that the best factorization is the one that minimizes total information. We began by looking for information-based metric so that we could say in some sense that the best factorization is the one that minimizes the total information for autoencoder and the data. Unfortunately, this total information did not generally correlate with subjective feature interpretability or activation sparsity. Runs whose feature activation had an average L0 norm in hundreds, but wait. What is L1 penalty? Oh, penalty is the sum of absolute value. Okay. So when we add absolute value, since a number is lower than 1 generally, absolute value looks sharply. Okay. Is there L zero penalty? Penalizes a number of non-zero entities. That is even stronger. I don't know why they didn't use it, but that should be a good reason. Okay, we began looking for information-based metrics. Wow. Now the attempts to use dictionary learning or sparse coding methods to automatically discover feature. I have run a major challenge. These methods require one to pick a number of features to attempt to decompose the feature into. But how can one know if they have picked the right number to get all the features without splitting a two feature into many parts? I mean, okay, sure. A recent report by somebody proposes Sharky proposes some heuristic, but answer seems non-obvious. Best factorization is the one that minimizes the total information of the encoder and data. Unfortunately, this information did not generally correlate with subjective feature interpretability or active velocity. Run whose feature activation had an average L0 norm in the hundreds, but low reconstruction error could have low total information. Okay. Thus, we ended by with a combination of several additional metrics manual inspection due to the features interpretable feature density. We found that the number of live features and the percent of tokens on which they fire are an extremely useful guide. Reconsider how okay, try model having a model which we know the ground truth, so I can cleanly evaluate autonomous performance was crucial in our early progress. Okay, I'm going to copy you here. Interpreting or measuring some of these signals might be difficult though. For instance, at various points we saw features which at first didn't make any sense, but with deeper inspection that we could understand. Likewise, while we have identified some disser, disserata, what things wanted or needed, okay, desirable things for the distribution, there are much that we still don't understand. Okay, sure. We think it would be very helpful if we could identify better metrics for dictionary learning from sparse outer encoders, trains, and transformers. Features which seem like bugs, single token features. When we limit dictionary learning, we say very few learned sparse features. The features that emerge sometimes look quite strange. In particular, there are a large number of high activation magnitude features which fired only fire on a single token and which seem to fire on every instance of the token. Such features are strange because the model could achieve the same effect entirely by learning different bigram statistics and so should have no reason to devote MLP capacity to this. Similarly, similar features are also recently observed in report by Smith. We believe that feature splitting explains this phenomenon. The model hasn't learned a single feature firing on the letter P. For instance, rather, it's learned many features which fire on P in different contexts, with correspondingly different effects on neuron activation and output logics as see below. As sufficient course level dictionary learning cannot tell the difference between these, but when we allow it to use more learned sparse features, the features split and refine into a zoo of different P. Okay, I mean, did I correctly understand them? No, but we move on. The one model we are studying. We choose to study a one-layer transform model. I mean, is this thing open source? I mean, maybe not here. We'll go here. We'll go here. We go and we'll go anthropic one layer transformer model. One layer transformer equal to a set of open source okay, bro. Wait, what does one layer transform actually mean? What is one layer? What does one layer transformer model in this paper mean? What is one layered? Is it a head? Okay. Refers to the transformer architecture. There's only one self-attention layer. Self-attention layer and one feed-forward layer. Really? One self-attention layer? Really? Wait, what does that mean? Does that mean it has one head? So there is only one head, right? Yes, okay. We choose to study a one-layer transform model. We use this model as a test bed for dictionary learning. Okay, one-layer models are small. They likely have true features rather than a large model, meaning features learned by small dictionaries might cover all these true features. We can highly overtrain one single transformer quite cheaply. We hypothesize that a very high number of trained tokens may allow our model to learn cleaner representation in supervision. We can easily analyze the effect features have on logic outputs because these are approximately linear. Analyze the effect features have on logic outputs. This provides helpful collaboration. We trained on two-layer transformers. We trained two one-layer transformers with the same hyperparameter and data set differ only in random series of initialization. We learn dictionaries and the okay why the same hyperparameter but trying on the activation of different tokens for each transformer. We refer this to the main transformer. We study the paper as transformer A and primarily this other transformer to study feature universality. Okay, we can compare the features how similar they are. Okay, interface for exploring features. Okay, the claim of the paper is a dictionary learning can extract features that are significantly more monosemantic than neurons. In this section, I'll have you here somewhere. The feature we study respond to text written with Arabic script. Okay, the feature. Okay, DNA sequences like this. Base 64 strings. Like the final characters in this thing. Text written in Hebrew script. For each learned feature, we attempt to establish the following claims. The learned feature activates with highly specificity for the hypothesized context. The learned feature activates with high sensitivity. Okay. To, to demonstrate claims 1 to 3, we devise a computational process for each context. Numericals. The full description. In this section, I'm going to summarize this. In this section, we primarily study the learned feature, which is most active in each context. There are typically or other feature that the model Okay. Typically, Monosemanticity involves a feature firing in many unrelated cases. If we show that a feature activates only when a proxy is active, we rule out this typical Monosemanticity. When features are more specific than the proxy, we often see multiple features work together to fill the space. Okay. The features in length are monosemantic, but some models have relatively monosemantic neurons. Okay. 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 This indicates that we are discovering something more general about how one-layer transformers learn representation of the dataset. We are discovering something more general. Okay, you are just talking. Okay, explain each of these guys. Graph analysis. The previous sections, if the previous sections persuaded you that at least some of the features genuinely interpretable and reflect the underlying model mechanics, it's natural to wonder how broadly these also serve outside of cherry pick features. The primary focus of this session will be to answer how interpretable the rest of the features. We will show that both humans and LM find out our feature to be significantly more interpretable than neurons, and quite interpretable in absolute terms. We show that both humans and LMs find out features to be significantly more interpretable than neurons. Okay. There are a number of questions one might ask. To what extent is the dictionary learning discovering all the features? Uh, 164 order. Okay. In this session, we will study different methods to analyze how interpretable neurons and compare neurons. Human analysis tend to from automated interpretability. All three approaches find that the features are much more interpretable than neurons. Okay, so you can understand what a feature means. When I talk about feature, I'm thinking of a bunch of neurons working together. But you don't exactly know what one neuron means. Oh, that's very interesting. It is very hard to interpret the meaning of one neuron, but very easy to understand the working of a bunch of neurons. That's cool. It is very hard to interpret the working of one neuron, but much easier to interpret the working of a feature, which is bunch of neurons. That's cool too. Manual human analysis 5%, we don't have any metrics, we trust more than human judgment. Thus a blinded annotator, one of the author, score features and neurons based on how interpretable they are. The score and rubric can be found in the appendix. Okay. In doing this evaluation, we wanted to avoid a weakness we perceived in our previous work, prior work, of focusing evaluations predominantly on maximal dataset examples. Many polysemantic neurons appear monosemantic if you only look at the top dataset examples, but are revealed to be polysemantic. If you look at the lower parts of the activation spectrum to avoid this, we draw simple uniform across a spectrum of feature activations and score each interval separately in light of the overall hypothesis. Unfortunately, this approach is labor intensive, and so the number of scored can be small. There are 412 feature activation intervals were scored across 162 features and neurons. And interpretability rubric value features neurons. Okay. They use the stones to destroy the stones. Okay. Like with the human analysis, we use the samples across a full range of activation to evaluate monosemanticity. Concurrently, for each feature, we compared the Spearman correlation coefficient. And I don't understand that. Automated interpreted logic weights, activation analysis caveats are manual and automated interpreter explain a few caveats. Feature activations are skewed towards lower intervals. Most feature activations are quite small and fall in the lower, less interpretable feature interval. That said, as we found our detailed analysis, most effects of a feature is due to higher activations. Next one, the evaluated features are sampled uniformly from among the set of all features, and interpretability might be correlated with importance. Man, this is getting harder. How much of the model does our interpretation explain? Okay, that's one. We now turn to the question we are least able to answer. Okay. To what extent does our seemingly interpretable features suppress the full story of the MLP? One could imagine posing the question variety of way. What fraction of the MLP loss contribution have we made interpretable? How much of the model's behavior can we understand? Is there if there really are some discrete set of true features, what fractions have we discovered? Uh Additionally, we summarize this thing. Okay. For example, the paper is a challenge of determining how much. Okay. For example, in A1 run, 79% of log likelihood loss reduction from the MLP layer is explained by the features and can improve with more features or lower L1 coefficient. However, measuring loss explanations this way may be misleading as more features are required to explain more loss. Some features may not be entirely monosemantic or cleanly interpretable. Despite the issue, the feature appear to influence model behavior in meaningful ways. The author suggests that automated interpreting could offer better measures, though it would be computationally expensive. They conclude that the defining effective metrics and efficient computation methods for evaluating feature-based interpretation remain an open challenge. Do features tell us about the model or the data? Oh, that's also interesting. The activation of a model reflects both the dataset's distribution and the model's transformation on the data. Oh, okay, both. Okay, cool. I think I read this part, right? Dictionary learning on activations combine these properties, making it challenging to determine whether observed feature stems from the data correlation or the model itself. To explore this, the author used a version of the model with random weights. Finding the feature derived from the model are less interpretable, especially on multi-token features. This suggests that the model's learning process creates a richer structure in the activations than the dataset distribution alone. The interpretability of downstream features effect is assessed using three methods. What does this mean? I think I looked up this too. Oh yeah, feature model. What kind of feature do you find them all? Okay, cool. Okay, feature spreading. We conjecture that there is some idealized set of features that dictionary learning would return if provided it with unlimited dictionary size. Oh, often these true features are clustered into similar set of features which the model put in a very tight superposition. Because a number of features are restricted, dictionary learning instead returns features which cover approximately the same data as ideal features. Other topics are somewhat less specific. Hmm. In the picture, okay. All right, I think that's it, right? Okay, how universal do, okay, this question is only one, okay, earlier. Let me put you two here. Comparing features between one layer transformers. But the features universal across different models is crucial. Universality suggests that features are not merely artifacts of dictionary learning process, but consistent reproducible unit of analysis. This would support the hypothesis the models are finite discrete set of features in the super question. The study found significantly universal. Okay, okay, cool. Yeah, I think I don't want to read that part. I think I'm going to stop it right here. Yeah, thank you for watching. Yeah, in the when I read the second, but I think I want to read this part also. All right, I'm going to end it right here. Thank you. I also have a work now. And thank you for watching.